All right, so hello everyone. I'm Yi, and this series of videos is really created to show you how we could use these package to create simulation for active structures. So to be honest, this is intended to be used as my group's internal training material, but I feel that it's such a good resource, and I really should make it open access and publish online so that everyone will be able to have access to it. So we're going to be focusing on active structures, or there are other terms like adaptive structures, architected structures, reconfigurable structures. There are a lot of these names, but then if essentially we're going to be focusing on a structure system that can change their configurations for different functionalities. So they can achieve shape morphing and get the reconfigure themselves into different shapes to achieve different functions so that they can adapt to the changing environment or the user need better than some of the more passive systems like the bridges that usually aren't able to do large deformation. So there are a couple of forms of these active structures like tensegrity, origami, active trusses, some of the shape morphing mechanisms, or even some smaller scale MEMS structures. They usually could be seen as say active structures, and this system definitely have broad applications in civil engineering. So before we get started with any technical stuff, let me actually show you a little bit more like what these code packages are able to do. So with the help of these a couple of GIF animations that's generated and simulated with these simulation package to get an idea of eventually after all these series of videos where we're heading towards. So this first animation is the active truss. So it's the blue trusses are made of with some active material. So if you apply a stimulus, let's say the top trusses, they will contract and the bottom they will expand, and then you are able to get this curling motion out of it that's captured with the simulation. These second example here is a Binet linkage. So this is a this is actually this exact same linkage here that can undergo large deformation to change their configurations. And by adding some springs, you are also able to make it bistable, which is actually quite cool to play with. And then the third example is something I've been working with a great friend of mine, Jingyi, and what she's been doing is creating a foldable thick plate using origami and kirigami inspired designs that can fold itself into, say, a very compact configuration, and then you can deploy it, and it forms a flat plate with a unit like a uniform thickness, something pretty cool. And the fourth example that's created using these package that we're going to learn is the Kressling origami. You just compress it. It can undergo bistable mechanical behaviors, which is quite useful for a lot of interesting applications. So the final one is actually a micro mirror, a model that I work together with another professor in mechanical engineering. So what I've been using this system for is they will implant these micro mirror into the brain of a mice. So this thing is very small. It's less than 2 millimeter by 2 millimeter in its footprint. And they can use the mirror to redirect laser and to achieve scanning, and they can capture the activity of the mice brain while the mice is moving around. So that's some very cool objects, and these code is created to try to understand the basically the fundamental dynamic behaviors of a mirror like these, and how could we use that to achieve better performance. So I hope that gives you an overall idea of what kind of simulation we're going to be covering. And let me start to talk a little bit more about another key motivation behind creating these set of living textbook or these set of tutorial videos. So, so I've been working in these active structures for quite some times, and honestly, it's um, when I look back at my own PhD process, it's not easy because in order to understand and eventually create this type of simulation, it really needs, classes from many departments, and they're all scattered around. So to get started, I need some sort of finite element, right? But in a finite element class, you only talked about small deformation. And there's a lot of material in that class. It's a hard theory class, but then within just one semester, we can only go that far, right? Small deformation, quad element, that's it. That's usually where the class will end. Then after that, these things, the system that we've been looking at, they undergoes very large deformation. So I probably need to take some sort of nonlinear, which is exactly what happened to me. I took some nonlinear analysis class to learn about nonlinear algorithms to find the equilibrium position, both the implicit and explicit methods. But that class only focuses primarily on the solver side and aren't able to cover, let's say, material nonlinearity like plasticity or like large deformation triangle elements, how to formulate that. The nonlinear class will not cover those. So I end up taking, classes from math department just to learn more about how the solvers works, numerical linear algebra, and to get a better understanding of those aspects. And I also end up taking classes like plasticity or more advanced finite element just to learn those. So eventually it took 4, 5, or even 6 grad level classes to get the foundation to support me to eventually start coding these simulation myself and start working on this work. So that's a lot of work. And there's not yet a single class to begin the whole process. So it's kind of like exploring blindfolded and unable to identify. It would be very helpful to have one class that can go over to get kickstart everything. So that's one of the primary reason why I hope to get this started. So now that I have the opportunity to start my own group, I figured out it would be very helpful for my student to also have something to just get started working on some sort of research and not to spend so many time taking classes before kicking start the research. So that's really one of the big objective of creating all of these. So this will most likely become some sort of a gluing class that's bring together those scattered materials. And with that in mind, I would like to just talk a little bit more about the organization of these living textbook or all those sessions that you are seeing on the left. So basically, this is the introduction, section 1, and then the section 2, we will talk a little bit about coding, because, well, right now, if you want to work on mechanics, work on simulation, you'd better work on some sort of computational work, right? Analytical can only brings you that far, and if you want to really make big impact, these things need to be computational. Um, and that's something very cool. It's still very important to work on analytical and theories. I'm not saying that those are not important, but in order to really push things towards the apply side, we need these computational methods. So that's why we need coding, and also give us a lot of help in terms of getting and reinforcing our understanding with the mechanics, and we'll get to that later. So that's why in the section 2, we will go over some of the basic coding aspect and the organization of these code package. And after that, the sessions following that would be primarily break up into 2 types. The first is the example sessions. The second would be the theory sections. So we usually start with the example. And after that, I would like to bring in a little bit theory to explain what's going on in those calculation examples. And realistically, to just keep things concise, I will not be able to go very deep into those theory sections. But what I will do is I will point towards certain related classes that you might take if eventually you want to get better knowledge in that specific chunk of material. So that's what I would do. So for instance, for formulation of elements, maybe there will be finite element. If you want to learn more about other nonlinear solvers that I'm not going to be able to cover in the in certain sections, then it's going to be nonlinear analysis. It could also be other materials like numerical linear algebra, which is really cool, one of the core courses behind all the scientific computation that we've been doing to capture the behavior of all these mechanical and kinematical systems. All right, so that's what I would do. And then finally, using the package, this package is made open access on GitHub. So if you scan these QR code, you will end up at this particular web page. And let me move my video here. And after you end up here, you can just go to this green button and there's a download zip and you just download the entire package and then you can run that in MATLAB. So big shout out to my previous group. And really want to thank their support. So many of these work originate from these package, which is a simulator we built together to capture the multi-physical behavior of active origami systems. That's where all of these started. So I would like to thank and shout out to my advisor and the group, Evgeny Filipov, and also Mark Schenk, a couple of other collaborators who had helped us work on this package. It had 31 stars. I didn't realize that, but then apparently people are using it. Some people are using it. But anyway, going back to these new package, you will be able to download it here. As always, we try to make all our code open access, which is something I really believe in. I strongly believe in that. And then after that, you do if in order to run this live code textbook, you will want to use the MATLAB version as 2024A or newer, because if you use older version, there's a chance that you won't be able to run it basically. So what we will do is while we are working on the materials, we will be defining functions um, in the write-up text. So we define functions when we need it. But then in the older version of MATLAB, you aren't able to define functions in the middle of a file. So all the function needs to be defined at the bottom of a file, and that's not good for the flow of a textbook or like something you want to read and understand what's going on. So be sure to install the newer version of MATLAB, and that will help you to get this code run without any issue. So with that, that's all I have for the first section, the introduction, and starting next time, we will start to work on the structure representation and the code organization of these particular package. All right, so thank you for your attention.